Hello, this is Robert, and in this video I would like to discuss the concept of polymorphism. C++ implements polymorphism by allowing us to use base pointers to create objects of derived classes. So in this example, I have the classic example, which is rectangles and boxes. So the box class inherits from the rectangle class. So a box is basically a rectangle with one more dimension, a height. So a rectangle has a length and a width, and a box has one more, the height. So you can see that we have two pointers, and they're both rectangle type pointers. And so those are base class pointers. C++ allows us, though, to create an object of the derived class if we want to, using the base class pointer. And so this allows us to do polymorphism. So even though we have two base class pointers, we're using one to create the base class object, which is a rectangle, and we're using the other to create the derived class object right there. So with late binding or runtime binding, the program will wait and decide which method to call at runtime. And so the way it works is it will check to see which object is being pointed to by this particular pointer. So at runtime it says, well, R1 is pointing at a rectangle object. So it will call the print version that goes with rectangle. R2 is pointing at a box, and so it analyzes this at runtime and it says, okay, I'm pointing at a box, so I will call the print version that goes with the box class, the derived class. So even though we have a base class pointer, it's going to analyze that at runtime and say, well, it's pointing to a derived class, so I will call the print version that goes with the derived class. Notice here that the output for the first version of print is for a rectangle, because that is the object that's being pointed to. The second version, we actually get the output for the derived class, which is a box. In the next part of this video, we'll take a look at the virtual keyword, and this is what makes all of this possible. Let's take a look at our classes now. Specifically, let's start with the rectangle class. So here's the header for the rectangle class. We have two methods declared in the public part, area and print. And then we have our getters and setters, our mutators, and our accessors. And then we have a couple of constructors, and then we have our destructor prototype. So we have several prototypes here, and then we have our private members here. So we have length and width, and then we have a C-string pointer or a char array pointer, char pointer, called base name. And we're going to be creating some dynamically allocated memory. When we take a look at the constructor, we'll see an example of how to create a dynamically allocated C-string. Okay, so that's the header for the rectangle class. Let's take a look at the implementation. The implementation is pretty straightforward for our accessors and mutators. The area is just the length times the width. Then we can set the length, set the width, get the length, get the width. And then we have our print method. Okay, so we're calling area inside of the print method. So this is a member function. So we'll be getting the area of this particular rectangle. And then we'll be accessing the base name here. And that's our dynamically allocated C-string that we're going to set in the constructor. So this is our default constructor. We know that it's the default because there are no parameters. And so when we create an object without any arguments or even without any parentheses, this is the default constructor that will be called, or it's not explicitly called, but so I guess it's triggered. I'm going to be using the word called, even though there is no explicit call to the constructor. Okay, so then we have a constructor that takes arguments right here. And you can see that we're passing in a length and a width, and so we're setting length to L, width to W. Then what we're going to do is we're going to set up our C string right here. So we're going to set aside a local variable, S length, and we're going to set that to the length of the word rectangle. Turns out that rectangle has 9 characters, so S length stores 9. When we create our C string using new, we're actually going to set aside 10 characters because we need 9 for the letters and then 1 additional location for the null terminator. Remember that C and C++ programs use the null terminator to figure out where the end of the string is. If they're not null terminated, then we could have a security issue. But even if we don't have a security issue, it's going to be some strange output because it's going to be outputting memory that wasn't set aside for the C string. Okay, so then what we're going to do is we're going to copy the word rectangle into the C string that we just created. And string ncopy takes 3 arguments, the destination, the source, and then how many characters to copy from the source to the destination. String ncopy isn't completely secure, so we have to make it secure by explicitly setting the last location in the C string to the null pointer. So we're explicitly null terminating our C string. Notice that I'm using S length here, and so that is index 9. We set aside 10 character locations, and then they go from 0 to 9, right? So index 9 is the last location in the array, and so we're null terminating our C string that way. The destructor is right here, and notice that it is used to free dynamically allocated memory. So first off, we ask if base name is equal to the null pointer, and if it's not, then we're going to free the memory that was allocated using that pointer. And notice that we're using the array version here. And then after we free that memory or delete that memory, then we're going to set base name equal to null. If we try to free memory that is null, like if base name did point to null or contained the null pointer, and if we tried to delete it at that point, our program could crash. So it's always a good idea to check if your pointer is not equal to null before you call delete on it. And then it's also a good idea to set it to the null pointer when you're done. Okay, so that is our base class. Let's take a look at the derived class now. So this is the header for the box class, and notice that I'm including the header for the rectangle class. This allows us to use rectangle as the base class. So now we say that box inherits from rectangle. We can also say that box is derived from rectangle. We also call it box the derived class and rectangle the base class. Okay, so we have an accessor for our height, and then we've overridden our area and print. Remember that if we have a member function that has the same name and the same signature as the base class, then we say that it is overridden. So area in the derived class for box is overriding area for the base class. Notice that the signatures are the same. The signature is that there are no parameters, so that's overriding. I could use overloading if I wanted to, or if we wanted to. We could put some arguments inside of the parentheses right there, and then that would be overloading. But since the signatures are the same, this is overriding. So then we have our accessor and our mutator. Then we have our constructors and the destructor, and then we have our private members. Remember that box is inheriting from rectangle. So box will inherit a length and a width. All we have to add for the derived class is the height. Okay, let's take a look at the implementation file now. And we have our mutator for height right there. And then we should have our accessor method. Let's see. Actually, I haven't implemented an accessor method. Okay, so then we have our area, and then we have our print method defined right there. Then we have our default constructor, and then we have the constructor that takes arguments. We'll take a look at that in just a moment. Let's focus on area for just a moment here. Remember that length and width were declared as private in the base class. So that means that even though box inherits from rectangle, they're still off limits, even to the derived class. So for the implementation of the area function right here, we have to use the accessors to get access to length and width, even though the length and width are part of the box object. Okay. So then what we do is once we know the length and the width, then we return the length times the width times the height. And if we take a look at our output down here, we can see that, that a box with a length of 3, a width of 4, and a height of 5 would give us a volume of 60. Okay, in a similar way, we have to call getLength and getWidth in the print method. And then we're just outputting our derived name, the length, the width, the height, and then we are going to output the area of a box. And so I'm calling area here inside of a member of box. And so area is also going to be the version that goes with box. Okay, so we're calling a member function right there. Notice that we couldn't access length and width directly because it's private in rectangle, but height is not. Height is part of a box. So we can see height right there. So height is a member and print is also a member. So because print is a member of box, it has access to all of the properties or member variables that are also part of box. So we can directly access height right there. We don't have to use an accessor. Then we have our default constructor, and then we have our constructor that takes arguments. Notice that in this version, we're passing 3 arguments to the box constructor, but we have to pass 2 of those on to the constructor for the base class, rectangle. So we're using the 3rd argument to set the member height right here. But since length and width are private to the rectangle, we have to pass those arguments on to the rectangle constructor, the version of the constructor that takes 2 arguments. If you prefer, you can put this base class constructor call on the same line if you would like. Okay, and then we have the destructor for the box class, which just frees our dynamically allocated memory right there. In the next part of this video, we're going to revisit the virtual keyword, and we're going to see what we get when the virtual keyword is used, and then I'm going to delete the virtual keyword and show you what happens when it's not there. So here we are back in our main function, and I previously explained why we got different output down here. We got box for R2 and we got rectangle for R1. And that was late binding, and it examined which kind of an object these pointers were pointing to, and it decided what to do at runtime. And I said that all of that was made possible by this keyword virtual. Let's go ahead and remove that keyword virtual. So now if we compile this program, it's going to do what is called early binding or compile time binding. That means that the program is going to figure out what to do when it reaches these method calls at compile time. So it's actually going to write it into the code which method is going to be called. Since the program can't decide what to do at runtime anymore, the only way it can decide what to do is to examine the type of the pointers that we have. So we have two base class pointers, R1 and R2. So when we call print with R1, the compiler says, well, that is a rectangle pointer, so I will use the print that goes with the rectangle class. Then it gets to this version also, and it says, well, that's a rectangle pointer as well, so I will use the print method that goes with the rectangle class. Even though R2 it was used to create a box object, it's actually going to call the base class version of print because we are no longer doing late binding. So let's run this version and we'll see that we're not going to get a box for output anymore. We're actually going to get output for a rectangle. So here's the output for R2 right there. Even though we are actually creating a box with the R2 pointer, since we're no longer doing late binding, it will give us the rectangle version right there. Okay, that is what happens when we remove the virtual keyword. So virtual goes in front of the method that you want to have late binding, like that. Okay, in the next part of this video, we're going to take a look at why we have virtual in front of the destructor right there. Okay, so we've taken a look at the two binding times, late binding or runtime, and early binding or compile time binding. And that's all controlled with that virtual keyword right there. Turns out that virtual in front of the destructor is there for a slightly different reason. If we don't have a virtual destructor, we might have a memory leak in our code when the program terminates. So let's take a look at what we get with the virtual keyword in front of the destructor. If I want to see the destructor in action, what I can do is I can put a breakpoint on the delete statement. So box is created using R2. So I want to set the breakpoint on this statement right here. So when I run this program, the debugger will take over and it will allow the code to stop on this statement right here. If I would like to see the execution of the destructor, all I need to do is step into it. So if you're using Visual Studio, the key that you want to press to step into it is F11. But since I'm using Xcode, I can step into it by clicking that button right there. So notice that the destructor for the box class was triggered first or called first. And so if we step through this, this destructor, we will free the memory that was dynamically allocated, and then notice that the destructor for the base class is automatically called. We don't have to do anything special to invoke the base class destructor. It just happens automatically. The derived class destructor will trigger the base class destructor. Okay, so we will we will free the memory that was dynamically allocated, and then we will return to the destructor for the derived class. So you can see that the destructor for the derived class actually invoked the destructor for the base class. And then the program is done. It's important that the memory is freed in the derived class, and then it's also important to free the memory that might have been allocated in the base class destructor. Because remember that when we create an object that is derived, for example, when we create a box, we're actually allocating the height, which was 5, inside of the derived constructor, but the length and the width were set in the base class constructor. So since box used two constructors, one for the derived class and one for the base class, we also have to do the same thing when we delete an object. So we have to use the destructor for the derived class, and then we have to call the destructor for the base class as well. So let's go ahead and remove that virtual keyword from the the base class here, and we'll see what kind of behavior we get with our breakpoint. So I'm going to run this program again, and when it gets to our breakpoint, I'm going to click Step into it. But this time, you'll notice that it's not going to call the destructor for the box class. Even though R2 is pointing at a box object, it's actually not going to call the box destructor. It just jumped right to the base class destructor, and it's only going to free the string that we created in the base class constructor. It's not going to free the memory that we created in the derived class constructor. So we're actually going to be skipping over some dynamic memory that we should have freed but didn't. So this is actually a memory leak because we are not calling the derived class destructor. So that's why it is very important that when we are using base class pointers to create derived class objects like we're doing here with box, it's very important that we use the virtual keyword in front of the destructor in the base class. So I need this virtual keyword right there to avoid a memory leak. Okay, so the virtual keyword in front of the destructor makes sure that the derived class destructor is invoked and also the base class destructor is also invoked. And so this way we won't have any memory leaks. Okay, I hope this video made some sense, and we'll see you next time.